Okay, we are back to more set theory. What we'll be talking about today is how to take the product of two sets, what that means, and how it is useful. We define the Cartesian product of two sets A and B as the set A times B, which is all ordered pairs or vectors where the first component is from A and the second component is from B. A big example we are all familiar with is the Cartesian plane. R2 is R times R, since it is the set of ordered pairs of real numbers. Cartesian products are just a generalization of the Cartesian plane to arbitrary sets. The Cartesian plane is named after René Descartes. Descartes was one of the major founders of modern Western philosophy, and in particular was the founder of the school of rationalism, which basically says that sensation and perception are illusions, and that truth can only be found in a metaphysical mind or soul, which is contained in every human. If you want a concrete example of what Cartesianism is as a philosophy, just think of the original Matrix trilogy. Matrix is Descartes plus Kung Fu.
Analytic geometry.
Show me.
But more related to the topic of our course, Descartes had a huge influence on the modern development of mathematics. Specifically, he developed the connection between analysis and geometry, but showing that geometric shapes had natural descriptions using equations and vice versa. All of this comes from the Cartesian plane. Here's a theorem that justifies a bit why we call this a product. If A and B are finite sets, then the size of the product A times B is the size of A times the size of B. Basically, the size of the product is the product of the sizes. To see this, let us say that A is size n and B is size m. Let us write out the elements of A and B as follows. The first row is pairs that have the first entry A1 and the second entry ranging over B. There are m of these. The second row is pairs with the first entry A2 and the second entry ranging over B. There are m of those. Continuing, we see that each row will have m entries and there are going to be n rows. So there are m times n elements here. Here's an example inside R2. Let A and B be closed intervals. A is the interval A1 to A2 and B is the interval B1 to B2. We can see from the picture that the product of these two intervals is a rectangle in the plane. In general, whenever A and B are intervals, then A times B is a rectangle. We can also ask, what is the complement of A times B? It is the entire plane minus a rectangle. And note that it is not a Cartesian product. More on this in a moment. We might be tempted to say that the complement of A times B is the complement of A times the complement of B, but this is false. For example, note that A times B is all of the pairs where the first component is in A and the second component is in B. On the other hand, A times B complement are pairs where it is not true that the first complement is in A and the second component is in B, but using De Morgan's laws, this is the set of points such that the first component is not in A or the second component is not in B. Whereas A complement times B complement is a set of points where the first component is not in A and the second component is not in B. Here's a concrete example. Let us consider E, the set of even numbers, inside the integers. The complement of E is O, the set of odd numbers. So E times E is the set of vectors where both components are even. The complement of this set is the set of vectors where one or more of the components is odd. More specifically, the complement of E times E is actually E times O union O times E union O times O. Not a single product, but a union of products. This generalizes nicely, and you'll see this idea again on a homework problem soon. Here's a nice short theorem. If A1 is a subset of A2 and B1 is a subset of B2, then A1 times B1 is a subset of A2 times B2. To see this, let the pair AB be in A1 times B1. This means that A is in A1 and B is in B1. But since A1 is a subset of A2, this means that A is in A2. Since B1 is a subset of B2, this means that B is in B2. Therefore, the pair AB is in A2 times B2. We have another theorem. The statement is complicated, but it's a useful theorem. It says that the union of A times B and C times D is a subset of the product of A union C and B union D. Let's prove this. Take the pair XY in the union on the left-hand side. That means that XY is in A times B or it's in C times D. Let's do this by cases. Assume that XY is in A times B. That means X is in A and Y is in B. But then, of course, X is in A union C and Y is in B union D, and therefore XY is in the right-hand side. The case where XY is in C times D is very similar. It's worth pointing out in general, the subset mentioned in the theorem is a proper subset. For example, consider the following picture. The right-hand side is the entire big rectangle, whereas the left-hand side is just the top left and bottom right smaller rectangles. We're now going to finish on one big example. It's a very cool example. Let E be the smallest subset of the naturals cross the naturals with the following three properties. Property A, the pair 1, 1 is in E. Property B, if any pair AB is in E, then BA is in E. And then finally, property C, if AB is in E, then A plus B is in E. This is clearly a non-empty subset of n cross n. But what is it exactly? Let us define G as a set of all pairs of relatively prime natural numbers. That is to say, all m and n in the integers such that the GCD of m and n is 1. The theorem that we're going to prove is that the set E and the set G are the same. Now, it's going to take a lot of work to get there from here. So before we start, a few words on why we might bother. Notice that if this theorem is true, then we have two different descriptions of a set. The definition of E is a purely algorithmic one. One could imagine writing a computer program to iteratively generate all the elements of E, giving the three properties above. The set G is an explicit global definition in terms of a single property. We're going to show that these are the same. And it's always good when you can show that a single object has two descriptions, because this gives a deeper understanding of the underlying object in the first place. We will first prove a series of lemmas that will get us to the main theorem. Lemma 1. The greatest common divisor of x and y is the same as the greatest common divisor of x and x plus y. To see this, we note two facts. Number 1, if d divides x and d divides y, then d divides x plus y. Moreover, if d divides x and d divides x plus y, then d divides y, because y is x plus y minus x. Therefore, the pair xy and the pair x plus y have exactly the same common divisors. Since the sets of common divisors are the same for each pair, the greatest common divisor of each pair must be the same. Lemma 2. For all n in the naturals, 1, n and n, 1 are both in E. We're first going to prove that 1, n is in E by induction. Okay, notice for the base case n equals 1, this is just property 1. Now assume that 1, k is in E. Then by property 3, 1, 1 plus k is in E, and this gives us the induction step. Also, notice that if 1, n is in E, then by property 2, n, 1 is in E. And we have proved the lemma. Okay, now lemma 3. If the pair AB is in E, then A and A plus B is in E for any n a natural number. Again, we will prove by induction. The base case is just property 3. Now let us assume that AB in E implies AKA plus B is also in E. Then using property 3, this means that the pair A plus KA plus B is in E, but this is just A K plus 1A plus B, and we have it by induction. Okay, now for lemma 4. If x equals q times y plus r, and yr is in E, then xy is in E. To prove this, let's assume that y, r is in E. By lemma 3, this implies that y, qy plus r is in E, or yx is in E. But by property 2, this implies that xy is in E, and we are done. Okay, now we're ready to prove the theorem. The claim of the theorem is that the set E and the set G are the same set. And almost as always, whenever we want to prove that two sets are equal, we prove one is a subset of the other, and then we go the other way. So first, let us prove that E is a subset of G. This means that any pair Mn in E must be relatively prime. So note by lemma 1, properties 2 and 3 of the definition of E preserve the GCD of any pair. In other words, if we ever take a pair of integers and apply property 2 or property 3 to it, we do not change the greatest common divisor. And we start with the pair 1, 1. That means that any pair that arises from a finite number of applications of property 2 and property 3 must have the same greatest common divisor as the pair 1, 1, and that clearly has the greatest common divisor of 1. This means that any pair that arises from the operations in properties 2 and 3 will always have greatest common divisor 1. So we are done. Now we want to prove that G is a subset of E. Assume that M and N are relatively prime. Now apply the Euclidean algorithm. M is Q0 N plus R1, N is Q1 R1 plus R2, R1 is Q2 R2 plus R3, and continue on and on and on until we get a term with remainder 1. Remember that we are guaranteed to get a term of remainder 1 at some point because the greatest common divisor of M and N is in fact 1. Now just reverse all the steps that we have just calculated in the Euclidean algorithm and we'll get the result. So first we know that the pair R sub n, comma 1 is in E by lemma 2. But now notice that Rn minus 1 is Qn times Rn plus Rn plus 1. What this implies is that the pair Rn minus 1, Rn, is in E. But since Rn minus 2 equals Qn minus 1, Rn minus 1 plus Rn, this means that the pair Rn minus 1, Rn minus 2 is in E, and by property 2, that means Rn minus 2, Rn minus 1 is in E. Basically, we just keep going back up the Euclidean algorithm chain. Every time we go up one level, we apply lemma 3 and lemma 2, and it tells us that the pair we have at one level implies that the pair at the next level is also in E. Since this holds for any pair that eventually gives us a GCD of 1, we are done. Okay, that was a lot of work, and it's good to stop there.